Okay. Hi, my name is Becca Miles. I am a sophomore at CCP majoring in biology.
I'm Keean Mansour. I'm a sophomore at CCP currently studying engineering. So the mesosphere is a portion of the atmosphere that is currently largely unexplored. Aircraft such as weather balloons and airplanes can't travel to it, and satellites can't really dip low enough. It's important to understand temperature and other climate factors of the mesosphere to influence travel to and from space and understand the environment overall better.
So our mentor, Dr. Zadi, and his colleagues developed these nanostructured centimeter scale discs, and they, because of their different surface structure, a thin mylar film with carbon nanotubes deposited on the underside, particles striking the surface leave the underside at a faster rate than those leaving the top, and this process creates a upward lift.
So we decided to produce a resistance temperature detector, or an RTD, to gather data in the mesosphere, as they can be produced with minimal weight using thin films and require very little power. They operate using the total voltage output of the simple circuit and calculating the resistance of the semiconductor portion using a Wheatstone bridge. Traditionally, RTDs are made with platinum because of its linear relationship between temperature and resistance, but we settled on silicon because of its lightweight and its heightened sensitivity.
So using MATLAB, I learned some coding and was able to come up with these graphs just showing the parameters we would need to achieve the voltage output we would desire for the sensor.
So based on Becca's graphs, I drafted a number of designs for these sensors, and the one I've settled on can be seen here. The yellow portion will be used for an etch process, and the green portion shown will be used for a liftoff process. So the etch process will begin with a lithography process using photosensitive materials. Using the mask shown in the last slide, we'll expose our wafer, develop it, and finally etch and strip, leaving the wafer shown here on the right. So the second portion of the fabrication process is called liftoff. This process is done by repeating the lithography step with slightly different chemicals, depositing chromium and gold in tandem using electron beam evaporation, and ultrasonicating to remove some of the photoresist and undesired chromium and gold, leaving what you see here on the right with our finished sensors that will eventually be diced into individual sensors for testing. The final sensors will weigh somewhere around 10 micrograms, which is well within the payload capacity of the flyers previously discussed.
Okay. To power the sensor, we'd be using a solar cell. To do that, I used a PN wafer, which is a wafer with a PN junction for the electrical current, using plasma-enhanced chemical vapor deposition, sputtering, lithography process, and etching. I deposited anti-reflective layer and aluminum contacts to create the solar cell.
So my favorite part about this process was actually collaborating with everyone. Working with my lab partner, Becca here, has been great. My fellow interns, being able to work with the principal scientists such as like Sam and Jason has been amazing, and producing my mask and my final sensor based on the input of everyone around me has been a real treat, and I think a huge experience that I can carry on to other facets of my life after this.
And I've really enjoyed the entire process of learning, trying new things. I definitely had a lot of hands-on experience in the lab, learned some coding, and everyone here has just been very helpful and motivating to keep pursuing science as a career to help with the future of the planet.